もしやコスモでは。
Cosmo makes me feel.
コスモ AP ラグジュアリースポーツ。
Welcome to part 47 of my 76 Mazda Cosmo restoration. The viewers have spoken, and through a poll on my Patreon, they decided that this episode is going to be about converting this classic 70s Cosmo dash to electronic. And I'm planning on using a bunch of this stuff right here. The original gauges are a combination of mechanical, such as the speedometer, odometer, and the clock, and electric, such as the tach, temperature, fuel, and warning lights. My goal is to convert the existing meter movements to tiny micro stepper motors, replace much of the backlighting with individually addressable RGB LEDs, and probably integrate some screens to replace some of the other warning lights. And to do this, I have a table full of goodies. We have a variety of individually addressable LEDs in square, circular, strip, individual. I love these things. Additionally, a selection of screens, LCD, TFT, OLED, and a selection of tiny stepper motors, which incidentally are the exact same OEM motors that GM, Nissan, and Nissan use in their gauge clusters. Now, one thing I want to be abundantly clear on is that I am not going to turn this dash into some garish show car nightmare. This little light show is just for the benefit of being cool. I do not intend to in any way violate the original styling of this dash, just modernize it and make it cooler. The instrument cluster and the bezel are what I'm going to be concentrating on. But before I go any further with the instrument cluster, I just want to make sure that I get the CAN bus data out of my MS3 Pro. So I have here an Arduino Uno and a CAN bus shield, and I turned on CAN broadcasting. And with a simple program that reads a few values from the CAN bus and dumps into the serial port, I can see that I'm getting data. Nothing special here about the program. I basically copy and pasted it from the library example and made a few tweaks. I think the easiest one to start with is going to be the tach, since it is just a needle. Maybe it comes out from the back. Well, this is rather interesting. The OEM tach meter movement is really nothing more than a voltmeter driven by what I assume is a very simple frequency to voltage converter, probably an RC circuit driving a transistor here, that just takes the pulses from the tach and converts it to a very low voltage, which drives this meter needle. Neat. So this is going to be replaced by this tiny stepper motor and the associated circuitry to drive it. So I need to mount this motor on a board and then build a little bracket to hold it the appropriate height so that the shaft sticks through the gauge face, stick a needle on it, and done. Right, because it's just that easy. Just pulling this board off because, well, we really don't need it anymore. And I think I'm going to have to cut into this gauge cluster just a little bit. Oh, look at that. The OEM gauge backlights were kind of blue. As I said before, normally these needles just pop right off. And I'm going to pull the speedometer out as well just to see, before I start on the tach, how similar it may or may not be. In case I have to just simply make two of everything. Not even remotely the same. Ooh, well, okay, that's broken. So much for being delicate. Yep. Oh, this used to be such a nice little precision build instrument. I feel kind of dirty doing that. Just a little dab of hot glue to hold this motor temporarily in place. I did briefly consider not hot gluing, because hot glue should never be used in a car, but epoxying the motor in place. However, I want it to be removable in case it needs to be replaced or for whatever reason. So I'm going to mill a Z-shaped bracket out of this aluminum. Seven millimeters. Just bring the end mill a hair above 7 millimeters and set the stop. And I'm going to mill out this entire area here down to the stop. It'll take a bunch of passes. My calibrated eyeball, plus all the measuring I did off camera, says that's about where the holes need to be drilled. Quick and dirty trick if you want to locate some holes but are too lazy to measure and set everything up. Put the bit backwards into the jaws. Then twiddle your knobs until the bit is in the hole. Lock your X and Y down. Rotate the bit into the proper direction. Just drill your hole. Now the back of this needs to be undercut in order to float over the motor. And I want to do it to the height of the bushing over the shaft, which is about 3 millimeters. Man, I really have to change this thing to a proper metric scale. Need to cut a relief for the existing bracket, so just scribe the lines as best I can. Taking a bit more trimming and a bit more filing till everything fits as it should. Hey, that actually worked.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its continuing mission to explore strange new worlds.
There we go. I removed this little thing for access to this hole unimpeded. That could be what she said. And I'll just trace out the center of the gauge face. Now the position of this hole doesn't have to be completely perfect, as it just has to provide room for the shaft to stick through, and the motor will not center on this hole. Since I have to clearance the back of this to fit the stepper motor, I was concerned I didn't have enough material, so easy enough to add some. Now that the motor can nestle snugly in place, just mark the mounting hole areas. This one. Oh my God, they actually line up. Just some slight countersinks so the screw heads won't interfere with the gauge face. A lot of work to make this thing that more and more looks like the Enterprise D, but now it's time to assemble it all. Remember that the circuit board was removed, so I'm going to use these two washers to make up the thickness. Now the stepper motor. These are just some tiny screws I had on hand, but what I'm going to do is hit the fastener store and get some longer ones so I can put nuts on the other end. Now the stock face support. Now the Enterprise. Yes, this is the first time I have tried to put all of this together, and I'm doing it live on camera. Finally, the gauge face. Wow! There we go. Only minor issue is it's not quite sitting flush, but that's just because of one of those little plastic nubbins. I will trim that. Betcha the engineer who designed this didn't ever think there'd be a tiny stepper motor in it. Now I grabbed the needle from the speedometer and it fits reasonably well. One stepper motor powered tech. I couldn't resist seeing it work, so I whipped up a quick stepper motor controller with an Arduino Uno and an HR4988 stepper controller. Of course, I put the schematics on my website, link in the description. The 4988 stepper controller is really easy to use. Just set one pin high or low to set the direction and pulse the step pin to move the motor. So we define the step and direction pins and then a pin to read the potentiometer value from. 680 is my best guess at the number of steps to move the motor fully zero to fully clockwise. We keep track of the motor position and the motor direction, two friendly names for the motor direction as opposed to saying high and low. This is a microsecond delay between step commands to let the motor physically move. Then a few variables to store the potentiometer readings. And finally a timer variable because we're going to check the pot once every second. So it starts by setting the pins as output. Then we write to the direction pin the value associated with counterclockwise. Then basically loop from 0 to the maximum number of steps, that's 680, writing the step pin high, waiting for 375 microseconds, writing it low, then waiting again. That moves the motor fully clockwise. Wait for 25 milliseconds, and then do the exact opposite to move the motor fully back to 0. That way the needle goes from 0 to full to 0, thus always making sure it starts at 0 no matter the position it was when the power was turned off. We make sure reset the motor position counter to 0, take a clock reading, and if 1,000 milliseconds has passed since the last clock reading, we note down the clock reading and read the potentiometer. Now it can jitter a bit, so only if the value has changed by more than 6. I use the map function to take the potentiometer reading that goes from 0 to 1023 and map it to values between 0 and 680, which honestly I think internally is just a linear equation. Or save this pot position. To actually move the motor, it's a pretty simple matter of just looking at the position of the pot, and if it's greater than the position of the motor, we're going to set the direction to clockwise, and then go through our procedure to step the motor by setting the direction, writing high to the step pin, waiting 375 microseconds, writing low, waiting 375 microseconds, then updating the position by adding one, and then looping back up to the top and doing that until this condition is met, and thus the motor has moved to the position set by the pot. To go the other direction, honestly, exact opposite. If the position of the motor is less than the position of the pot, set the direction to counterclockwise and step, subtracting one from motor position, back up to the loop, and rinse and repeat until it's done. Of course, all that code is on my website. Let's power it up. And now to twiddle the pot. Red line and idle. And red line and idle. That's an idle. Of course, remember the needle is jerking it around like that because my little demo only checks the position of the pot every second or so. You could do this for hours. A little bit of glue holds the odometer reading so that I don't have to write it down nor remember it. The odometer shaft is held in by these tiny little crimps. Once again, I thought about not gutting this stock gauge, but this little frame is almost perfect for what I intend to do. In case you've ever wanted to know how one of these worked, the speedometer cable drives this cup. Inside there's a magnet. That magnet spins, introducing a current in this copper, which magnetizes it and causes it to pull against this spring and rotate the needle. Here's the magnet, and these gears run off of the shaft as well and turn the odometers. I wish there was a more elegant way to have done that. Well, after a bit more off-camera hacking, cutting, and grinding, I'm left with what I want, which is this frame. And just like the tack, the frame is the only thing that I really need. The speedometer presents a slight issue in that there are two odometers. And if I use the same stepper I did with the tack, once it is in place, there's no room for anything to run the odometers. So, as she said, the solution is always a longer shaft in the hole. And with this different style motor, I now have plenty of room for odometers. And how awesome would it be if these holes lined up? 4 millimeters would save me a lot of work. So what I'm going to do here is mill a C-channel shaped piece out of this chunk of aluminum that fits right inside here. That will support the stepper motor. trim it down to size. I rough cut the width on the bandsaw, and I will make the final adjustment on the mill. Well, now to make the holes that secure it to the speedometer bracket. Mounting holes. So because I'm going to tap these holes out to M4, I don't have a lot of margin of error, so I'll use the mill to drill them as accurately as I can. That is a terrible noise. And now I will just ream the threads out of the existing holes. Now finally, it's time to mount the motor. And let's face it, if it is off a millimeter, doesn't matter. Carefully remove that. Hold the motor down and mark the holes. It's kind of amazing, but ever since I got this thing, I'm finally able to drill a straight hole. Is that what she said? Or he said? I don't know, someone said it. And now assembly, starting with the long, tiny screws for the motor. Oh, that is lost forever. Surprisingly, I have a 4mm socket. And now the gauge face bracket. Sweet! Now during assembly I noticed one minor issue. Once this piece is welded on, it's going to be virtually impossible to get the motor in there and the bracket and whatnot. There's a very specific sequence of assembly in order to get the motor in as this top piece is welded on. So the aluminum bracket goes in, The motor slips underneath. Just enough play to offer a little bit of adjustment so this can be perfectly centered. On final assembly, there will be some nuts on the top of the motor, but for mock-up here, it can just be stuck in. Wonderful. And you'll notice I've attached some temporary wires so that it can be tested. Of course, now we want to see it work. So I've connected it up to the same Arduino-based test rig I used on the TAC. One bit of difference though is that these Nissan steppers seem quite a bit slower than the GM steppers I used in the TAC, so I had to about double the step delay in my code. In a great irony, the stock speedometer needle didn't fit the stepper motor, so I used some tape. But as I turn the pot, the needle moves. At 88 miles per hour, we're going to see some serious shit. Without the mechanical odometers, the reset button has nothing to activate. Now, I had hoped that I could make use of this as a knob by modifying the existing actuator here, but nope. Because this here is the location of the button, and that witness mark up there is where it presses on the reset mechanism. Now, if I was just going to stick a button under there, that'd be no problem. But see, I wanted to give this knob a little bit extra functionality by adding one of these. A rotary encoder. Don't need this thing anymore. Rotary encoders are used behind most modern dials and simply just pulse these pins in a specific order when they're turned left or when they're turned right. And then this one has a built-in button that is activated on these pins when it's pressed. Awesome, it fits right in. Almost like I spent hours looking over rotary encoder datasheets and picked the exact part I needed. No, not really. I just bought 10 of the cheapest rotary encoders I could find on DigiKey that had push buttons. That came out pretty easy. The plan is to make a little adapter out of this steel rod, which will turn this tip into a slotted screwdriver to engage the rotary encoder. If you don't have a lathe, the trick I learned a few years ago when drilling a hole down a rod is to chuck it up in the mill or drill press, clamp it into the vise, bring the chuck off of it, and now drill your hole because it will be perfectly centered. I need to weld the little knob rod to the piece I just drilled, and the best way I can think of keeping it straight is to just use the mill to hold it. Now I'm going to just freehand carefully shave this into what's basically a flathead screwdriver bit. I did this by eye. I mean, we're talking an assembly that will move in fractions of an RPM. I think there should be just enough friction for a test fit. Yep, definitely some friction there. Not quite straight, but there we go. Back and forth, and button. Seems about right. So we'll just trim it about here. And the middle of the shaft is at about 7 millimeters. So this is where I'm drilling for the shaft. Okay, need to trim about 13 millimeters off of this. Well, I'd say I need a hole right about here. There is no way in hell I'm going to get a drill in there. So I bent up this piece of welding rod and I think I'm just going to heat it and melt through. Well, that seems to work. It's as tight as the Vatican's legal files in here, so there's kind of a very specific way to assemble this. Kind of force the bolt in. Finally, insert the encoder with the nut and washer. Now that is going to need a little bit of adjustment and clearancing, possibly some straightening, but one Pretty versatile, awesome control. Now that I have a knob to twiddle, back to the speedometer, which of course needs odometers. And that's why I have these LCD screens. And I think that's where we'll leave it for now. There's still a lot of work to do, including finishing the rest of the gauges and designing the circuit to control it all. But we'll pick that up next time.